Let's open up the textbook and see where it actually starts. Scrolling down, we finally get to Chapter 1. Chapter 1 is called Introduction, the Nature of Science and Physics, and it starts right here on page 5. Notice that the page number is 5, but my PDF viewer identifies this as 15 out of 1422 up at the top. In my videos and examples, I will always refer to the actual page numbers written on the pages themselves, like 5 in this case. With that, let's get started. First, let's define what physics is. According to Wikipedia, physics is the natural science that involves the study of matter and its motion through space and time, along with related concepts such as energy and force. One of the most fundamental scientific disciplines, the main goal of physics is to understand how the universe behaves. I would add that not only is our goal to understand how the universe behaves, but also why it behaves this way. There's something very rewarding about discovering that what looks complex and confusing at first is really being caused by basic, simple rules that we can understand. A lot of people identify the first modern physicist as being Galileo Galilei, born in 1564, who is, for some reason, known by his first name. Galileo liked to test things by doing simple experiments. For example, he once famously dropped 2 spheres from the Leaning Tower of Pisa to test whether the more massive sphere would drop faster. Surprisingly, he found that they both dropped at about the same rate. Galileo then went on to postulate that if it were not for the complication of air resistance, gravity would cause all objects to fall at the same rate, even a bowling ball and a feather. To prove this quite visually, in 2014, Professor Brian Cox visited the world's biggest vacuum chamber in Ohio. He and his crew attached a bowling ball and a large feather to electromagnets on the ceiling of a giant room in which they were able to pump out the air. They pushed a button which released both objects at the same time, and they observed both objects falling at exactly the same rate. Normally, since the feather has a very small mass, it's greatly affected by small forces, such as wind and the motion of falling through the air, and that's what slows it down as it falls. On the other hand, a very massive object like a bowling ball might feel the same forces of the air, but its motion is hardly affected at all. That's why the bowling ball falls almost as if the air wasn't there at all. Another famous physicist who made a lot of progress was Isaac Newton. He wrote a book called the Principia, which laid the foundations for what we now call classical mechanics. The Principia included 3 laws of motion, now called Newton's laws, and the law of universal gravitation, which states that all massive objects attract one another. Apparently, Newton's inspiration for this last one came to him one day while he was outside under an apple tree, looking up at the moon. He knew that in order for objects to go around in a circular path, they had to have some force pulling them in towards the center, like this ball in a string. The string pulls the ball inward, and if you let go of the string, the ball no longer travels in a circle. Newton knew that the moon orbited the Earth in almost a circular path, meaning there had to be some force pulling it inward toward the Earth. Suddenly, an apple fell from the tree. Newton realized that a familiar force, gravity, had just pulled the apple toward the center of the Earth. Perhaps the same force was what pulled the moon inward, keeping it in its orbit around the Earth. Aha! Indeed, it turned out to be exactly correct. Gravity is a universal force that pulls all massive objects toward each other, and it explains the observed motion of the moon around the Earth around the sun, and even the sun around the center of the galaxy. Okay, that's enough history for today. I'd like to spend the rest of this video going over some basic terminology that's often used in physics and other sciences. Let's start with the word model. In science, a model is an idea or picture in our minds which helps us understand and predict things in the real world. For example, this drawing is a very simplified model of a lithium-7 atom. An atom is a tiny little thing, much too small for anyone to actually see, and it almost certainly doesn't really look like this. But experiments on actual lithium lead us to believe that each neutral lithium-7 atom is composed of 4 neutrons and 3 protons, represented by blue and red spheres in this model, all packed into an extremely tiny nucleus, plus the 3 electrons orbiting around it. One tool that we use a lot in scientific models is math. We write down equations, such as the famous E equals mc squared, to help us understand and predict things. Many equations can be represented on a graph of y versus x. Y is typically plotted on the vertical axis and x on the horizontal axis. If your equation has some x's on the right-hand side, then for every value of x you try, you can compute a corresponding value of y. And then you can put a red dot on your graph at just the right xy coordinates. This online equation grapher, to which there's a link below, lets you play around with this particular equation, y equals ax squared plus bx plus c. Here we take 3 input numbers, a, b, and c, and it gives us a particular red line. A is multiplied by x squared, b is multiplied by x, and then both those products are added to c to give y. The graph starts with a, b, and c all 0. In this case, no matter what the value of x is, y is always 0. So your red line is a flat horizontal line right along y equals 0. If you slide the c up and down, the red line goes up and down. If you slide the b up and down, you will see that for positive values of b, the red line slopes upward to the right. Higher values of x give higher values of y. For negative values of b, the red line slopes downward to the right, meaning higher values of x give lower values of y. Lastly, you can try playing with the value of a. It sets the curviness of this line. If a is 0, the line isn't curved at all. If a is positive, the line is said to be concave up, curving up like a bowl or valley. If a is negative, the line is said to be concave down, curving the other way, like a hill. Now, let's introduce another term called the scientific method. You have probably heard of this, and there are many attempts online and in various textbooks to define what the general method is that scientists use. It always has something to do with making theories and testing them with experiments. Here's one 4-step summary of the scientific method that I like. Step 1 is you make careful observations of the world and ask good questions so you are familiar with trends, repeatable phenomena, and previous discoveries. Basically, you become an expert on something by really looking at it a lot. Step 2 is you generate a hypothesis and make predictions based on the hypothesis. For this step, you might have to use mathematical models, cartoon pictures like that drawing of an atom, etc., to really describe your hypothesis. Step 3 is you perform experiments, which test the hypothesis and might disprove your theories. Lastly, step 4 of the scientific method is to use the detailed results of your experiments to refine and revise your old theories and to ask new questions. And this kind of brings you around to step 1 again. And of course, don't forget to publish your results so other scientists can learn from what you did. Next, let's talk about physical quantities and units. We define a physical quantity either by specifying how it is measured or by stating how it is calculated from other measurements. Measurements of physical quantities are expressed in terms of units, which are standardized values. Without standardized units, it would be extremely difficult for scientists to express and compare measured values in a meaningful way. The textbook includes this drawing of a guy looking at a treasure map, and the scale of the map lists a distance called 1 cable. The guy wants to know how far he's going to have to travel to get to the treasure, which makes him think, I wonder how big a cable is. Too bad the map maker didn't use some standard unit of length that the map reader also knew about. This brings us to an accepted set of units used by almost all scientists on the planet called SI, which stands for the French phrase Système International. SI includes 4 fundamental units. Length is measured in meters, mass is measured in kilograms, time is measured in seconds, and electric current is measured in amperes. All other physical quantities can be expressed as algebraic combinations of length, mass, time, and current. These are called derived units. An example would be the unit for speed. Speed is computed by taking a length and dividing it by a time. So, the SI units are meters divided by seconds, or meters per second. Okay, now let's give it a try. Imagine a rectangular football field has a length of 100 meters and a width of 60 meters. The equation for the area of a rectangle is length multiplied by width. So, what is the area of a football field? Notice that since 100 times 60 is 6,000, the numerical part of this answer is 6,000. But that's true for A, B, C, D, and E. What's different about these different multiple choices is not the number part, but the units part. 4 out of 5 of these answers have the wrong units after the 6,000. I'd like you to take a moment now to pause this video, look at this list, carefully review what we've talked about so far, and decide on an answer before proceeding. Okay, we're back. And it turns out the correct answer is D. The area is 6,000 meters squared. One way of looking at this is to put the 100 and the 60 meters in parentheses and then apply our rules of multiplying to rearrange the factors so you have 6,000 times meters times meters. Meters times meters is meters squared, so it's 6,000 meters squared. Let's think for a bit about the physical quantity of time. It is said that Galileo used to measure time by feeling his own pulse, and he believed that his resting pulse was close to 1 beat per second. So for Galileo, beats and seconds were basically the same thing. But different people have different resting heart rates, so this is not a great way to measure time. Stopwatches are a lot better. But how can we be sure that they're all exactly the same? Well, it turns out that atoms have fundamental vibrations due to the orbits of the electrons. And we can measure this. Scientists are able to measure a particular frequency of cesium atoms to a great precision, and this gives us what we call atomic clocks. The SI unit of time, the second, is by definition the time required for about 9 billion vibrations of a cesium atom, and there's the exact number. And it turns out that light in a vacuum always travels at a very exact speed, which is about 300,000 kilometers per second. So if we know exactly how long a second is, we can define a meter in terms of how far light travels in a certain number of seconds. In SI units, the meter is defined to be the distance light travels in about 1/300 millionths of a second in a vacuum. And the last fundamental SI unit we use a lot is the unit for mass, the kilogram. It turns out that the kilogram, or 1,000 grams, is defined to be the mass of a particular platinum iridium cylinder kept at the International Bureau of Weights and Measures near Paris. Exact replicas of the standard kilogram are kept at various locations around the world, including one just up the road from me at the National Research Council Meteorology Laboratory in Ottawa, Ontario. Now, It's not always very convenient to state numbers in terms of millions, billions, billionths, etc. So we have prefixes in SI which represent various multiples of 10, which we call orders of magnitude. For example, 10 to the power 9 is 1 with 9 zeros after it, or a billion. If we have a billion bytes of information, for example, we call this 1 gigabyte. We call a billion meters a gigameter, etc. Similarly, mega means million and kilo means 1,000. We also have prefixes for the orders of magnitude that are less than 1. For example, 1 over 100 is 10 to the power negative 2, which represents 1 with the decimal place moved 2 steps to the left, or 0.01. This is represented by the prefix of C, which stands for centi. For example, 0.01 meters, or 10 to the minus 2 meters, is 1 centimeter, which is about that much. Similarly, milli means 10 to the minus 3, micro means 10 to the minus 6, and nano means 10 to the minus 9. Often, in science, it's necessary to convert from one type of unit to another. For example, what if we wanted to convert 80 meters into kilometers? One way of doing this is to use a conversion factor of 1. A conversion factor of 1 is a ratio expressing how many of one unit are equal to another unit. In this case, we know that 1,000 meters is the same as 1 kilometer. So our conversion factor can be either 1 kilometer over 1,000 meters or 1,000 meters over 1 kilometers. To convert 80 meters into kilometers, we need to multiply by something that has the meters on the bottom. So the meters cancel the meters in the 80 meters. Then we just multiply 80 times 1, then divide by 1,000 to get 0.08. And the units of that are kilometers. Now you give it a try. Let's say you know your height is 65 inches and you want to convert that to centimeters. You also know that 2.5 centimeters is the same as 1 inch. Which of these two conversion factors would you multiply your height by in inches to get your height in centimeters? Please pause the video now, think about this, review what we've learned so far, and when you have an answer, resume the video and I'll tell you my answer. Okay, we're back. And if you chose A, you're correct. Both of these conversion factors equal 1, which is good. But if you're starting with 65 inches, you need to multiply by something with inches on the bottom, so they can cancel with the inches on the top. When you do this, you get 65 times 2.54 divided by 1. These inches cancel, and you get 165 centimeters.